Hello there, Mr. Vessel here again to look at another AP Statistics problem from the 2013 exam, this one number 3, and the theme of this task is normal distributions and also combining distributions that are normal. So that's what this task is about, kind of an interesting set of parts here. So we're going to dive in and check this one out. The right up here is about eggs here, so I got information about each full carton of grade A eggs consists of 1 randomly selected empty cardboard container and 12 randomly selected eggs. And the weights of such full cartons are approximately normal. Obviously that's an important phrase. And we get the mean of 840, and the standard deviation is 7.9. And the first part is, what is the probability that a randomly selected full carton of grade A eggs will weigh more than 850 grams? And while this is possible to do without a sketch, I really find a little sketch goes a long way with this kind of task. So I'm going to draw this one out. And we know it was normal with mu is 840 grams and sigma is 7.9 grams. So the sketch can be the tool that you use to show how you get your answer, how you're calculating it, and it really is a great tool that you can use. And it's also maybe a little easier than using some notation sometimes. But basically, what you want to be able to do is just show the grader that you know what you're talking about. So we're looking for 850 or more, and in a normal distribution, we just want to draw something symmetric. It doesn't need to be the perfect scale, but we're just trying to find this probability, this shaded region here. And in order to do that, since it's normal, we can use our z-score formula here. Z equals x minus mu over sigma. So in this case, we really have everything we need to calculate z, and we're just going to look that number up in our z-score chart here. But first, let's calculate the z-score. So in this case, z is 850 minus 840 over 7.9, and just as a reminder, z tells us the number of standard deviations above or below the mean. So in this case, we can find our z-score, and if you round it to 2 decimals, it comes up to be 1.27 here. And you could totally use a calculator or some other technology to look this z-score up, but when you just use the chart, use the table in this case, we're just going to use 2 decimals, and this should look familiar. But what I want to find here is the z-score that corresponds to 1.27, which is right here, 0.8980. And just as a reminder, this is the probability that the shaded region will be below that particular z-score. So while the 8980 is going to be useful, it's not the answer to the question. The 8980 is everything that I don't want, actually. It's the probability that the full carton of eggs would be under 850 grams. So this answer here is 1 minus 0.8980, or 1020. Oops. So a little over 10%. And again, this is full credit on an AP exam. You've got the sketch. You've got to show how you calculate z. We've shown that we've looked up z, and one thing that might be nice to add here is this is also where the z-score is located at 1.27 standard deviations above the mean. I always like to just kind of summarize it down here, though. So the probability that a full carton of grade A eggs more than 850 is 1020. And so once we have this calculation, part A is finished. We've got that one completed. Basically, it was a normal distribution problem where we just want to find a z-score and look that z-score up, either in a table or using some sort of technology. The second part little more challenging usually for this kind of task. What part B is getting at is using the full containers and kind of breaking it down into its pieces. So it says the weights of the empty cardboard containers have a mean of 20 grams and the standard deviation of 1.7. It is reasonable to assume independence between the weights of the empty cardboard containers and the weights of the eggs. It's also reasonable to assume independence among the weights of the 12 eggs that are randomly selected for a full carton. And let X represent the weight of a single randomly selected egg. And it's asking us two parts. What's the mean of X? What's the standard deviation of X? So, basically what this part is getting at is taking this full carton. Remember from before, the mean for the total was 840. And the standard deviation for the total was 7.9. But what the total is 12 eggs plus a carton, an empty carton. And what we're given in the second part here is we're told that the mean of the carton is 20 grams. We're told that the standard deviation of the carton is 1.7 grams. These are all in grams too. And what this task is really about is just what happens when you combine distributions. So you can consider this total egg carton with the 12 eggs and the empty carton to be a sum of 13 different things. You've got the carton itself, and then you've got each egg, which is independent of each other and randomly selected. So basically what we're going to try to do is break down this total into its 13 components to figure out what will the mean of a single egg be, along with what is the standard deviation of a single egg. So the task here, I think it helps to kind of break this down here. Something that we know in general about means. So the mean for the total has to be equal to the mean of the carton, and I'm going to define. It says X, right? X is a single egg, so I'm going to use their same lettering. They told us that what we're going to try to find is mean of X. That's something. We're going to try to figure that guy out. We're going to try to figure out the standard deviation of X also. That'll be a separate deal, but we're going to try to find both of these things. So in order to do that, what we do know about the total is that we have to add 1, 2, 11, and 12 eggs to this particular carton. So this is 12 items. And once we can kind of lay this out and sort of think about this in terms of its pieces, that if I took the carton plus 12 of these eggs, that I would have the total, this calculation's not so bad because we know all these numbers and we can calculate the mean for a single egg. So what we'll need to know is that we know this number is 840. We know this number is 20. And while we don't have this number exactly yet, we do know that there has to be 12 means of single eggs. This is a pretty straightforward algebra equation. We're just going to subtract the 20. So I know that 820 has to be the total of the 12 eggs. So now the mean of a single egg is just 820 over 12. And that number is 68.33 grams. I'm actually through repeating for grams. So a little over 68 grams is what a single egg will represent, or mean for a single egg is in this particular situation. And then the next piece, maybe a little more challenging, is working with the standard deviations. But again, I think sort of setting up something similar where we have some knowledge of how distributions combine, we can use a little algebra here to find the standard deviation as well. So what does that look like? Well, here's one thing that's really important. When you're combining distributions, it's really tempting to kind of want to work with standard deviations. But in general, when you combine distributions, and they need to be independent, that's why they wrote this prompt by saying that it is reasonable to assume independence in two different cases. But what's really important to remember is that variances add. This is true if you're adding two distributions, subtracting two distributions, it doesn't matter, or even multiple. In this case, we have 13 different distributions that we're adding together. And it's going to look something like this here. So we know that the variance for the total has to equal the variance for a single carton. And similarly to before, we've got the variance of an egg. But we're going to have another egg and another egg and another egg, so we have the variance of 12 eggs. And we're going to do something similar to before, where we know a lot of these values. We're just going to be able to calculate, this has 12 of them, and we'll be able to calculate the variance of a single egg, which then in turn will get that standard deviation. So, using some of the same values, well, not same values from before, but we know that the variance of the total is 7.9 squared. 7.9 squared. So you do have to remember also that the standard deviation is a fine number, and it's more useful in most cases. We can interpret that. We know what that means. Variance is that value squared, and in this case 7.9 squared is the variance of the full carton with the 12 eggs. And the variance of an empty carton, that was provided also, that's 1.7. So we're going to square 1.7. And I have 12 variances for a single egg. I'm just going to use the letter X here. So a little bit of calculation here. We're going to take the 7.9 and subtract off the 1.7 squared. 7.9 squared minus 1.7 squared equals 12 variances for a single egg. This number comes out to be 59.52. You can check that in your calculator. And what we're going to end up doing with that is just dividing that number by 12 to get the variance of a single egg. When you divide that number by 12, you get 4.96 is the variance for X. So then we have one more step to do. We have to take that square root here. So the standard deviation for X is the square root of 4.96, which is 2.23 to the nearest hundredth grams here. So this was definitely one of the harder tasks. You know, a lot of times students have no problems with means and knowing that when you add or subtract distributions, that means will add or subtract. But working with variances is often a little more challenging, and there's more to pay attention to. Variances will always add, and then you can use that fact to, in this case, just solve for a missing piece here. So that's how the 2013 problem number 3 went. Thank you for checking this video out. I'd encourage you to check out some more videos that have to do with AP statistics. So thank you a bunch for your time, and if you like this video, please feel free to subscribe or check out some more. Thank you very much.